plus Eyj and then Ezq. So electric field is simply minus 6x plus 2 I hat and plus 0j and 0k. So this is simply minus 6x plus 2 I hat. This is the electric field. Now we want to find out this electric field at 300. So that would be x value is 3. So that is simply minus 6 3s are 18 and plus 2. Oh, so this is also minus, right? So this thing is also minus. And in here we have also minus, and in here we have also. So what do we have? This is minus 2, this is minus 2, this is minus 2. So 6 3s are 18 minus 2 minus 20 I hat. So this would be the electric field and magnitude would be simply 20. So we see that whenever we have the potential which is given, so from potential we can calculate the electric field. That was the idea of this question. If it is clear, please note it down. And if you guys have any doubts, please tell me. Otherwise, quickly note this thing down and then we'll talk about potential energy. Okay, so we have something clear. Good. Yeah, whenever you guys have noted it down, please tell me. Yes, noted, guys. Okay, so let me see if we have any other important questions. This is same, but this is a little complicated. So yeah, let's skip this question. So this is the same question. Now let us talk about potential energy. So what is this potential energy, right? So we talked about what is the relation between electric potential and electric field. Now let us talk about what is this potential energy. Okay, so right, so the potential energy is simply this is work done in making the system. Right, so this is what we call the potential energy. And for two charges, right? So let's say we have Q1 and Q2 charge. So for these two charges, potential energy is simply how much this is, let's say we have this Q1 and Q2 charge and they are separated by R. So potential energy is simply K Q1 Q2 by R. This is the potential energy, right? And if we have multiple charges, so if we have multiple charges, then potential energy is K Qi Qj, right? And this is summation and half, and then this is Rij. So this is this is the potential energy for multiple charges, right? And we will see how this is calculated. So we'll take one example and then we'll see how this is calculated. So let us take one example of a triangular charge, right? So we have three charges, and let's say this is Q1, let's say this is Q2, let's say this is Q3. And let's say this distance is R12, this distance is R23, and this distance is R1. Right. So what we have to do is that we have to count the contribution of two charges at a time. So if I pick this charge, right? If I pick this charge, so how many combination I take to make a pair? How many combination I take if I pick this charge? So if I pick this charge, then the two pairs that I can make from this charge is this one and this one. Right. So these are the pairs I can make. Right. So for Q1, I have two combinations. Now one more combination is left. So let's say if I pick this charge, I pick this charge. This one I have already counted, right? Q2, Q1 I have already counted, so this one is remaining. So for Q2, I have one combination. So in total, I have three combinations. Right. So in total, I have three combinations. So potential energy would be how much? This would be simply K Q1 Q2 divided by R12 plus this is K and Q1 and Q3 divided by R13, and then the last one is K Q2 Q3 divided by R23. So this would be the potential energy, right? Is it clear, guys? Is it clear? Good. So now we can also use this to find out the potential energy of four charges, right? So let's say, let us find out the potential energy of four charges. This is Q1, Q2, Q3, Q4. So can you guys tell me in total, how many combinations should be there? In total, how many contributions should be there? Yes, guys, in total, how many contributions should be there? Yes, guys, can anyone tell me how many contributions? So we saw that in here we had three combinations, right? We have to find out pairs. So Nabil is saying four. Good, Nabil. Nabil is saying four. And Iram and Alia, what do you guys think? So we have to take two pairs at a time, right? We have to take two pairs at a time. So potential energy would be due to two pairs of charges. So Nabil is saying that we can take four such kind of combinations. What do you guys, Iram and Alia, what do you guys think? Yes, any answer that please respond. Whatever answer is coming into your mind, right? Don't think whether it is right or wrong. So because then I would be able to understand that you guys have understood the previous part, right? So this is what I was talking about. The same idea we have to apply in here. Alia
So
is saying,
4.
okay, everybody is saying four. Okay, so Iram is also saying four. Okay, so let's see that, right? So first we have to one by one take the combination. So let's say if we choose this one. If we choose this one, so how many pairs we can make for Q1? For Q1, how many pairs? This one, and this one. These three are the pairs, right? Clear? For Q1, we have three pairs. For Q2, how many pairs there would be? How many pairs would be there? If I pick this one I have already counted. This one is there, and this one is there. Right, these two pairs. So I have two pairs. Now I have to come to this Q3 charge. So for Q3 charge, I have already counted out. I have already counted this one. I have already counted this one. So only this one is remaining. So for Q3, I have one pair. So in total, I have six pairs. Okay, is this part clear, guys? Is this part clear? Okay, so let's say if this is a square. So this is a square, so this is A, this is distance is A, this is A, this is A, and this distance would be root 2A. So now let us write all the potential energy. So potential energy would be how much? For Q1, that is K Q1 Q2 divided by A plus K Q1 Q4 divided by A, and then K Q1 and Q3 divided by root 2. So these are the potentials that I have. And then I have K Q2. So for Q2, I have Q3 by A, and K Q2 and Q4 by root 2. And then lastly, I have K Q3 Q4 divided by 8. So 1, 2, 3, 4, 5, and 6 combination. So these would be the combination, and what would be the final potential energy? So 1 by A is common, right? So I can take K by A, Q1 Q2 plus Q1 Q4 plus Q2 Q3 plus Q3 Q4 and plus K by root 2A, and this is Q2 Q4 plus Q1 Q3. So this would be the total potential energy. If it is clear, you guys quickly note this thing down, and then we'll talk about the other potential energy, right? So we have talked about potential energy due to two point charges. We have talked about potential energy due to multiple charges. And then we will talk about potential energy in an external electric field. Yeah. So whenever you guys have noted down this part, please tell. Yeah, whenever you guys have noted, please tell. And if you guys have still any doubts, please tell. Yes, noted, guys. Noting. Okay, yeah. So whenever you guys have noted, just tell. Done. Okay, so now let us talk about potential energy due to in an external electric field. Right, so this is simply, let's say we have electric field and we are calculating the potential energy of this Q charge and we are trying to find out what would be the potential energy of this Q charge in the presence of this electric field. So we know that this has a potential V at this point. So potential energy would be simply Q. This is the potential energy, right? And then we have, let's say if we have two charges, so let's say if we have a Q1 charge, if we have a Q2 charge. So then what is the potential energy? So potential energy is Q1, and at this point charge would be V1, potential V1 and potential V2. So Q1 V1 plus Q2 V2 plus there would be a potential energy due to these two charges. So that would be K Q1 Q2 divided by R. So this is the total potential energy for two charges. Right. And we have just seen that if we don't have any external electric field, so these things are zero and potential energy is simply K Q1 Q2 by R. So these are the potential energy. And then in the last, we have the potential energy due to a dipole. And how much is that? So this is minus P dot E. So this is the potential energy. What is the work done? So work done is simply minus P, and this is cos theta 2 minus cos theta 1. So this is the work done for the dipole in the external electric field, right? And this is minus Pe cos theta. The potential energy is simply minus Pe cos theta. So these are the things, these are the basic concepts of potential energy. And then I'll talk about the capacitor. So first, you guys quickly note down this part. And then I'll talk about capacitor. And then we'll do some questions of capacitor. And then we'll start the electric current chapter. So quickly note down these things. Yes, noted, guys. Noted, guys. And this is in external electric field, right? Okay, so now let us talk about the capacitor, right? So we all know that capacitor is so this is an energy storing device, right? And then what is so a capacitor, this has three kinds. One is parallel plate capacitor, and this is, oh, so yeah. And one is parallel plate capacitor. The other one is spherical capacitor. And the last one is cylindrical capacitor, which is not, so this is not we are doing, right? This is for JE syllabus. So this part is not. So we'll only talk about these two capacitors, right? So, and before we talk about this parallel plate and spherical plate capacitor, let us talk about what is capacitance. So capacitance is the proportionality constant, right? So we know that the Q is directly proportional to voltage. So if we remove this thing, so we'll have this constant, and this is what we call the capacitance, right? And this is, so C is simply Q by V. So this capacitance doesn't depend upon the charge. This doesn't depend upon the potential. So if we have this Q, we are increasing, but this capacitance would be same. If we are also increasing the voltage, so this capacitance will also become, will be the same, right? So this is a constant, right? This is a constant. This is a constant quantity. And this is a proportionality constant because the charge is directly proportional to the voltage applied. So now let us talk about, right? So this is the thing that we have to always remember, that C is Q by V. For a capacitance or for a capacitor, capacitance is simply the ratio of the charges and voltage. So that is the capacitance. Now let us talk about the parallel plate. So can you guys, this is represented as this thing. This is represented by two parallel lines, and this is how it is denoted. Or we can denote it by this thing also. So this is positive, and then this is negative, and this is earthing. So this is how we denote the parallel plate capacitor, right? Can you guys tell me what is the capacitance? So what is the capacitance of a parallel plate capacitor? Yes. Can you guys tell me what is the capacitance of a parallel plate capacitor? So this is, we don't need to just remember what is the derivation, but after derivation, this comes out to be A E epsilon naught by D, right? Where this A is the area of this plate, right? This is A, and then these are the separation, right? And this D is the separation between the plates. And epsilon naught because it is dependent upon the medium. So it is dependent upon the medium because this is, if this is air, so this is AE epsilon naught by D. In medium, so this is in air. And in medium, if you place a dielectric medium in between the plates, right? So let's say you have these two plates, and then you place a dielectric medium in between the plates. So then what would be the capacitance? So this is A, then this is D. So this capacitance would be simply AE by D. And what is this E? So this is AE epsilon naught K by D, where this K is dielectric constant, not the other one K. So this K is different. This is dielectric constant. Right, so these are the things that we have studied. And we have also studied that what is, so we have also studied that for partially filled capacitor, with dielectric material. So what is the capacitance? This is simply AE epsilon naught T minus D plus T by K. So this is the capacitance. So what you do is that you have these two capacitors, and then you place a partially filled a capacitor, right? So you place a partially, okay, this is not visible. Maybe this would be visible. So you place a partially filled dielectric with a thickness of T. So this is thickness and this is the distance between the plates. And this has a dielectric constant K. So this would be the capacitance, right? But if it is filled with, so if it is filled with conductor, then the capacitance is simply AE epsilon naught, and this is K, and this is D minus T, or T minus, so this is T minus T, I guess. Let me check what is that. And we will do all these questions, right? Okay, so this is D minus T plus T by K, and then this is D minus T. So yeah. So this would be D minus T, right? So D minus T, and this is also D minus T. Derivation is not important, right? Because we have to just remember these things. So you guys just note down these things and then we will do some questions. So please note down all these things. These things you guys have already discussed in your CBSE classes, right? So just note down all these things. And whenever you guys have noted it down, then please tell me. Yes, whenever you guys have noted, please tell me. Yes, noted, guys.
Yes, sir.
Okay, so then let us, yeah, so then let us quickly do this spherical capacitor. And then we will do all these questions. So we have this spherical capacitor, right? And then we have to find out. So then let's say what is the voltage of this thing? So charge on this thing is Q. And we know that what is the voltage on this, what is the potential on this sphere? So what is the potential? So potential is simply KQ by R, right? This is the radius. And we know that what is the capacitance? This is Q by V. So Q is this and KQ by R. So this R goes over here, this Q cancels. So this is R by Q. So R and K is 1 by 4 pi epsilon naught. So how much this thing would be? So capacitance is 4 pi epsilon naught. So if somebody asks that what is the capacitance of Earth, right? What is the capacitance of the Earth? So we can directly write that the capacitance of Earth this would be 4 pi epsilon naught and radius of the Earth is 6400 kilometer, right? So how much is this thing? 4 pi epsilon naught and 6400 kilometer is 10 to the power 3 meters, right? So we know that what is 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught is 9 into 10 to the power 9. So 4 pi epsilon naught is simply 1 by 9 into 10 to the power 9. So this is how much? 6400 into 10 to the power 3 divided by 9 into 10 to the power 9. So this would be how much? So this is 10 to the power 5, 64 by 9, and 10 to the power 5 minus 9. So this is how much? Nearly 7, and then 1. So this is 7.1 into 10 to the power minus 4. Right. And this is farad. So this would be the capacitance of the Earth. Okay. So quickly note down this thing and then we'll do all the other questions. Quickly note down this thing, guys.
Noted, sir.
Noted. Good. So now, yeah, we'll talk about the combination of capacitors later. But before we do that, let us do some questions. So that whatever topics we have done now, this would be okay. So let's do some question. This we have already understood, right? What is the potential due to multiple charges? This we have already understood. So yeah, and you can find out what is the potential for uh, n number of charges, right? So this is n into n minus 1. So I was asking that how many combination would be there? So if you have 5 charges, then this would be 5 into 5 minus 1 by 2. So that would be 5 into 4 by 2. So that is 10. So this, in this way, you can calculate how many combinations are there, right? So yeah, this one is the, yeah. And now let us, yeah. So this simple question is, good. And okay, do we need this thing? What is the work done in bringing three charges at a separation A by 2? Okay. Mm. So this question you can, and yeah, this we can also do. So okay, so now let us do this simple question. So we have three charges placed at the vertices of an equilateral triangle of side A. Find the potential energy of this distribution. So we have three charges, and they are Q charges. So Q, Q, and Q, right? And then we have the separation, which is A, and A. So we know that there are three charges. So how many contribution would be there? 3 minus 3 by minus 1 by 2. So this is 3 into 2 by 2. So this is 3. So let us write the potential energy. How much is that? So this is K QQ by A, and then K QQ by A, and then K QQ by A. So this would be the potential energy, and this is simply KQ square by A. So this would be the potential energy, right? And now we want to find out what is the work done in bringing. So this part we'll do, yeah, so let us do this part, and then you guys can note it down. So the next part is, what is the work done in bringing the three charges at a separation of A by 2. So now we are bringing all these three charges at this separation. So to calculate this thing, work done using the potential, this would be very lengthy, right? So this would be very lengthy, and we don't know what is the electric field. But we can use the idea of potential energy. So how we can use that? So whatever is the change in potential energy, right? Whatever is the change in potential energy, that would be the, so let's say we have this thing, work done would be the change in potential energy, right? So this would be U final minus U initial. Okay, so what would be this thing? So let's say this is for initial energy, we have already calculated, that is 3kq squared by A. Now what would be the final energy? So that would be kqq by A by 2. And then this is kqq by A by 2. So by goes here. And then kqq by A by 2. Right? Because the separation has become A by 2. So now the separation has become A by 2. So this is how much? 2, so this is 2 into 3. So 6kq squared by A. So work done would be simply 6kq squared by A minus 3kq squared by A. So this would be simply take q square by. This is the one. Okay, is it clear, guys? If it is clear, then please note down these two questions, right? Note down these two parts quickly, and whenever you guys have noted, please tell me. Yes. Yes, noted, guys. Okay, so now let us find another question, right? So this question is not needed for the, yeah, so skip this part, right? And then this one we have done. So yeah, so this one we can do. So what is the work done by on the dipole by rotating it from stable equilibrium to unstable equilibrium in the presence of electric field of magnitude 200 volt per meter, where P is 4 coulomb meter, right? So we want to find out what is the work done. What is the work done by the dipole by rotating it from stable equilibrium to unstable equilibrium in the presence of electric field where P is this thing, right? So we know that what is the work done. Work done is simply minus PE and cos theta 2 minus cos theta 1. So this is the work, right? P is given, E is given. We have to find out what is theta 2, what is theta 1. So theta 2 is the unstable equilibrium. Theta 1 is the stable equilibrium. So can you guys tell me what is the stable equilibrium? Yes. So for what case we have the stable equilibrium? We have this electric field and you have this dipole. and this is the dipole moment. This is the angle theta. So can you guys tell me, when do we have the stable equilibrium and when do we have the unstable equilibrium? So what is the stable equilibrium? Can you guys tell me, and what is the unstable equilibrium? Okay, so the stable equilibrium is when you put this dipole in this way, minus q to q, so that the angle is 0. So this is theta equals to 0. Unstable is when you put the dipole in this way, and this is minus q, and this is plus q. So then your angle becomes 180 degree. Right, so this is your angle. This is an electric field, so angle is 180. So this is theta 180. So theta 1, right? What is theta 1? Theta 1 is stable equilibrium, 0 degree. Theta 2 is unstable equilibrium, which is 180 degree. So then what would be the work? The work done is minus P is 4, electric field is 200, theta 2 cos 180 minus theta 1 cos 0. So this is minus 800 and minus 1 minus of 1. So this is minus 800 into minus 2. So minus 1600 and minus minus plus. So 1600 joules. So this would be 1.6 kilojoules. So this would be the work done. Is it clear? Is it clear, guys? Okay, good. So this is the work done, and in the second part, they want us to calculate the change in potential energy. So we know that change in potential energy is simply work done. So this would be also 1.6 kilojoule. Calculate the potential energy of dipole when it was kept at 60 degree. So third part is that we have to find out potential energy, and with this is, we know that this is minus PE cos theta. So minus 4, 200 and cos of 60. So this is minus 4 and 200, cos of 60 is 1 by 2. So this is minus of 800 joules. So this is the potential energy. Right. Okay, so please note down this problem, and then we'll talk about the capacitor. So these are the questions on potential energy. Yeah, whenever you guys have noted, please. Noted, guys. Yes, noted, guys. Yes, guys, noted. Yes, did you guys note it down? Noted, everyone. Okay, I guess you guys have noted, right? Yeah. And then this is all right about the potential energy. Then let us do some questions on capacitor and capacitance and capacitor, right? And before I do all these questions, so do I need to also talk about, yes, spherical capacitor we have done, right? And I want to talk about the Earth's capacitor, but so these are the two different capacitors, right? Okay, this thing is not important. And then, okay, yeah, so, okay, so let us understand all these things. Oh, so I have, oh, we have, so let us understand what is the energy stored in capacitor. Right. So what is this thing? Energy stored in capacitor is simply uh, this is Q, or this is, so this is Q square by 2C. This is Q square by 2C, or we can write this as half CV square, or this is half Q into V. So this is how we can write this thing, right? And depending upon the situation, we can use any of these three relations. So this is how we calculate the energy stored in a capacitor. Right. So this is how we calculate the energy stored in capacitor. And what is the energy density? So let us find out what is the energy density. Energy density, and this is, we are talking about energy density of a parallel plate capacitor. So how much is this thing? So energy density is denoted by small u, and this would be energy by volume. Right, so this is the energy density. So energy is how much? That is, let me write it as what? So let me write it as Q square by 2C. Right. And volume is area into the distance. So that is the volume. Right. So this is how much? Q square divided by A into D into 2C. Right. What is the capacitance of a capacitor? Q is, let us write it as Q, and this is 2A, D, and this is A E epsilon naught by T. So D and D will cancel, and we have Q square divided by 2A square and epsilon naught. So what is Q square by A square? What is Q square by A square? Yes. So Q by A is sigma. Right, Q by A is sigma. So this would be how much? U would be sigma square by 2 epsilon. Right. And we also know that how this sigma is related. So electric field of a capacitor, this is sigma by epsilon. So sigma is electric field and epsilon. So if you put this value in here, so this would be E square and epsilon naught square by 2 epsilon naught. So this will cancel and energy density would be half epsilon naught E square. So this is a very important relation. Right. So this is the energy stored and this is the energy density of the parallel plate capacitor. Please quickly note this thing down. And I will just quickly write the combination of capacitors and then we will do some questions. So this chapter will be completed. Yes, whenever you guys have noted, please tell. Yes, noted, guys. Okay, so now let us understand the combination of capacitors. So we have, let's say we have this thing. So we have series combination. Right, in series combination, what do we have? In series combination, let's say we have all the capacitors are alternatively connected. So this is how the capacitors are connected. Right, so this is plus, this is minus, this is plus, this is minus. So they are alternatively connected. Positive part is connected with this thing. So negative part is connected with positive, negative part is connected with positive, right? So this is how it is connected. So what is the effective capacitance? So this is in series combination, 1 by C effective or C equivalent. This would be 1 by C1 plus 1 by C2 plus 1 by C3. Let's say this has C1 capacitance, C2, C3, C4, and so on. So this would be the equivalent capacitance. In parallel combination, what do we have? So all the positive ones, right? All the positive ones are connected with the positive ones, right? So this is positive. And this is positive. So all the positive terminals are connected to the positive terminal. All the negative sides are connected to the negative side of the battery. So in this case, C equivalent is simply C1 plus C2 plus C3 and so on. So this is the effective capacitance, right? Equivalent capacitance. So this is all. And yeah, so this is all about the electric potential chapter. Right, we'll do some questions using this idea, but yeah. So let us. Okay, so yeah, just quickly note down this part and then we'll do some questions. So just quickly note down these things, right? Quickly note down these things and then we'll do some questions. Okay, whenever you guys have noted, just oh, two people have disconnected. So Nabil and Iram got disconnected. Yes, Alia, whenever you have noted, please tell. Noted, Adi.
Done.
Okay, so now using all these ideas, let us do some questions, right? So these are the things that we have just talked about, right? Okay, so yeah, need one is not needed. Okay, so now yeah, this question is important. So let us do this question. So what do we have is that let's do this question. Okay, so this is the question that there are two charges, right? Two spherical charges, and then they are connected together. So then the wire is connected between them. So then we have to find out what is the ratio of Q2 by Q1 charge, right? They have the radius R2 and R1. So if they are connected together, so the idea is that whenever the two spheres are connected, so their potential becomes equal. So potential on this surface becomes equal to potential on this surface. So let us do this question. The first part is we have to find out what is Q2 by Q1. So we know that potential becomes equal. So then what will happen? We know that V1 equals to V2. So V1 is how much? That is simply KQ1 by R1, and this is KQ2 by R. So K cancels, and Q2 by Q1 we have to find out. So Q2 is there, Q1 is taken in the denominator, and R2 goes in the other side. So this is R2 by R. So this would be Q2 by Q1, which is would be equal to R2 by R. So that is the idea, right? In the second part, we have to calculate the surface charge density ratio. We know that what is sigma. Sigma is Q by A, right? So sigma 2 would be Q2 by A2. This would be Q2 by Q1 by A1. So Q2 is, right, this is Q2 by Q1, and A1 is it goes in the top hand side, and this is A2. So Q2 by Q1 I already know. Q2 by Q1 is R2 by R. Area 1. So what is the area, surface area of the first sphere? That is 4 pi R1 square. And then area of the second is 4 pi R2 square. So this part cancels, R2 and R2 cancel, R1 and R1 cancel. So this is R1 by R. So this is sigma 2 by sigma 1, right? And then E2 by E1 we can also find out, but so let's just note down this problem, and then we'll then if we have time, so this chapter is over, right? So this chapter is over, and in the next class I will start the electric current, and I will try to also start the other chapters as well, right? So just note down from here. Just note down from here that these two spheres are connected with this wire. And then what is the ratio of Q2 by Q1, sigma 2 by sigma 1? E2 by E1, you try to figure it out, right? So you already know these things. E2 by E1, you try to figure it out. So, yeah. Just calculate these things and just note down this thing, and whenever we have noted, just tell me. And whenever you have noted, just tell me. Yes, noted.
Yes, sir.
Okay, so there are other